So FPGA-based key value stores really emerged in the context of distributed data analytics applications, and they are motivated by the separation between the compute layer and the storage layer, and they provide really a good balance between energy efficiency and in-storage processing capabilities within the storage layer. And as you are probably aware, there's numerous works coming out in the last few years in these topics, and I think they are convincing in that we can use FPGAs for data management and for high performance processing within the storage layer. But unfortunately, they don't really provide transactions. And this is a problem because if we want to kind of play with the adults, we need to make sure that we can provide kind of consistency for multi-key accesses. So what I argue for is that really for the next key value store design that we're doing, we should really take transactions into consideration and implement them. And the good news is that most of the key value store designs running on FPGAs today are already likely linearizable, and adding transactions on top is actually not something that is prohibitively expensive. So, in this sense, we're optimistic, but we of course have to go and implement transactions in real systems. So why I am saying that key value stores are already providing linearizable execution? Well, it all comes down to how requests are processed inside the core of the key value store. So usually there's multiple steps which can be carried out in parallel for different requests, and these are sending a command to the storage, getting some data back, and then taking decisions and writing it back to the storage. Now, to avoid so-called data hazards, which arise because of the high latency of the memory or storage medium, most of these solutions already include a so-called write-back buffer, which forwards changes, for instance, from this set to the get, which is executed concurrently, and this way avoiding hazards. This also means that unless the requests are reordered within this pipeline, the execution will be linearizable. So this is good news for a single client. This basically means serializable execution. But of course, if we have multiple clients, then things change a little bit. So with multiple clients, what we see is that because their requests are arriving over the network and they might have to be reconstructed from multiple network packets, they will be queued in different, let's say, staging FIFOs, right? And they will be scheduled in an interleave way as they arrive. So this means that they can see corrupted state, right? Now, one way to provide transactions, which is actually for free, is to wrap this request in a so-called transaction wrapper, right? So we're not acquiring any locks, we're just enforcing the scheduling of this request to happen one after the other without interleaving with the other client. So, this is something that can be done, and it will give us serializable execution, but it also brings drawbacks, namely that latencies will be very high if your request stuck behind a large transaction. So, while this is free, it should be used only sparingly for the occasional multi-set write, for instance, multi-key write, to ensure that these happen atomically. If we want to provide more, let's say, more interleaving for concurrent transactions, then we can do two-phase locking and snapshot isolation using a lock manager, which is a data structure and some logic to handle locking and unlocking keys. And this is feasible, but it brings some challenges. One challenge is that doing this locking and unlocking will be an inherently iterative operation, which, given the FPGA's low clock rates, could actually jeopardize bandwidth or jeopardize the throughput of the storage nodes. Luckily, however, we are interfacing with the network, so this defines a little bit the maximum throughput that we need to support and helps us design this functionality in a way that we fit within the time budget we have available. Then there's also the second challenge, which has to do with undoing transactions on the FPGA. Unfortunately, the on-chip resources are not sufficient to support arbitrarily undos. So what we can do instead is to rely on strict two-phase locking and snapshotization for reads to make sure that the locks are acquired in a way that once a transaction acquires all its locks, it will never fail. It can always commit. So to conclude, I think we all agree that transactions are needed for future key value stores built on FPGAs. And given that simple forms of transactions can be done almost for free, there's really no excuse not to include them in the next designs. And as I showed in the talk, and I talk about this in the paper, other forms of transactions which allow more interleaving, so they lower latency and increase the throughput of the system, are also very much within reach and should be considered. If you have comments, questions, or wish to collaborate, please feel free to reach out.